So we are given here the spin half state, which is written like this, which is the spin x eigenstate. This positive indicates the positive eigenvalue part. So how can we write this? As we have shown earlier, this is in terms of column matrix. First entry is 1. Here the second entry is 1. Okay, so this is the spin x eigenstate. And we need to evaluate this generalized uncertainty relation that we had previously derived. And there are some operators. That's why I said we need to see if this holds. So first we'll write this operators in bracket notation. So that will give us some clarity. So spin x operator takes me from minus state to plus state, or it will take me from minus to plus state. Similarly for spin y, there is a phase. So spin z is nothing but diagonal completely, so negative eigenvalue. Okay, yeah. So it can be easily checked that if I do the square of this part here, spin x operator, what will I get actually is these terms are multiplied with themselves. So there is plus minus multiplied with plus minus, and then again plus minus is multiplied with this minus plus, right? And the same part will be repeated. So this will be 0, and this term will give 1 because states are normalized. So what one can check is this. To get the same state, not same state, but it is equivalent to doing the identity operation. So there is plus plus, yes, plus minus, this is plus here. So we can say just this basically, you know, you do this twice, you're not doing anything. It's identity. Same goes for others as well. So I square is x square. So this can be easily checked. You'll get the same answer, right? Okay, so the first thing that we need to find is the expectation value of Sx. Since the eigenstate is of Sx plus operator only, I'll get the constant value of h bar by 2. So Sx is simply h bar by 2. Okay, then we need to find expectation value of Sx square. So we know this. Okay, and we know what is the Sx square operator. It is not going to do anything. So you can check one thing here. When Sx square operates on Sx plus, what it will give me is 1 by square root of 2 by 4, and this is an operator which will operate on state plus and minus. So what this, when this minus minus goes to this, it will give me 0, and when this minus minus goes to this, it will not change the state. So what it will give me is the same state, right? Okay, so when I multiply this again, so when I multiply this again, what will I have? I will have the same 1 by square root of 2 multiplied again and the same states. So it will be 1 by 2 h square by 4 square by 4 4 6 minus multiplied with plus minus. So I will have, there is this plus, this will give me 1, there is minus minus, it will give me again another 1. So square by 4. So we can say the uncertainty in Sx is square minus whole square, which is nothing but 0. This is h square by 2, h by 2, sorry. So we have h square by 4 minus h by 2 square, which is 0. And this is somewhat obvious because this is eigenstate of Sx operator. So delta Sx 0, right? Okay. For the sake of completeness, we can try to find the expectation value of Sy as well. So can write this. We know this is going to be h bar upon 2, and this is 6 plus how do we write Sy is negative I plus minus plus I, and there is 6 plus. So Sx plus contains linear combination of positive and negative. So when this will operate, how do we write this? Okay, so I'm just writing it here. By square root of 2, positive, negative, right? So these operators are supposed to swap the negative with positive. Okay, so this will change to negative, and this will change to positive with a face included. Okay, so what will we have is this I, and we have negative, then there is minus I, that will be positive. Okay, so yeah, we can keep the I outside, and there will be again a 1 by square root of 2, but this time we have positive plus negative multiplied with negative minus positive. So this will give us plus plus, which should account to 1 and plus negative 1 plus minus this is 0. So sy is also 0, right? So yeah, we can expect because these are not eigenstates of sy. But what one can see here is, since sy square is square by 4, not something else, is identity. So average value of sy square is equals to which are normalized states. So we get square by 4. So uncertainty y square is equals to y square minus r whole square equals to square by 4. And we can again write same thing for sz, since they are not eigenstates. Eigenstates of sx. So sz is equals to 0, but that square will give me square by 4. Okay. So what we need to see here, we need to check rather graph A average value of these objects is greater than or equal to 1 by 4. Square A is 1 sx, B is sy, if A is z, and B is sy. So that is 1. Since we are talking about multiplication, since we are multiplying, so for the case of this, this is 0, because there is no uncertainty in 6, so it's by default satisfied. In the case when is z, p is sy, so at that time You know that uncertainty in delta z square is h square by 4, and sz is 0. Similarly, delta s y square is also h square by 4. So yeah, their average values will be now. I need to see the commutator relation of sz and sy, which is going to be, well, it's, 6 sy h bar is z. So if this is replaced with z, this plus y will give me minus ih by 6. This is x y times z, so on. These are positive orders. So if I'm going from z to y, it will be negative. So this will be minus ih bar 6, and yeah, so RHS will be minus ih bar rid of sx squared times 1 by 4. So this is square by 4, and average value of sx will be dh bar by 2 squared by 4, 16. So they saturate each other. 16 and 16. Both sides are same. So we have verified